Hey Chemsters, this is Mrs. Vandeloy bringing you Chemster video for Chapter 6, Section 5 about polar molecules. Already in this chapter, we started off talking about bond polarity. And if you look over here, this is the idea of a bond polarity. How do we know this? You look on your periodic table that we gave you that has those electronegativity values in the bottom right-hand corner of each element, and then you subtract. So if you subtract the electronegativities, this is again a review, and you end up between 0 and 0.4. It is a pure nonpolar covalent bond. What does it say here? Electrons are shared equally, okay? But if you subtract and you get above 0.4, so let's say 0.5 up to roughly 2.0, all right, that's called a polar covalent bond, where electrons are shared unequally. And look at this right here. Look what happens. We've already referred this before. We end up with a partial negative and a partial positive. And how do you know which one's going to be partial positive, partial negative? Well, the one that loves electrons the most, the one with the highest electronegativity value, is going to be the partial negative. So the other one is going to be your partial positive. And if you don't read this, you should jot this down, okay? The one that loves electrons the most will be partial negative, the one that has a higher electronegativity, okay? And then if there is such a difference between the loving of electrons, between 2.0 and 4.0, it's going to be an ionic bond where the most electron loving one will get the full negative and the least electron loving will be a full positive. That means they lost electron. Are you sure? Yes, I am very positive they lost an electron. Ha, ha, ha. All right, so that's our quick review of bond polarity. So what about a polar molecule? All right, well, a polar molecule has polar bonds and are not symmetrical. And we're going to talk more about that on the next page, okay? So just for now, know what a polar molecule is. It has this uneven distribution of electrical charge throughout the entire molecule, all right? So what does this mean? The entire molecule, one end is slightly negative and the other end is slightly positive. And how do I write this slightly? Do you see this up here? That's that Greek letter partial, which is a delta, lowercase delta in the Greek alphabet. So it means partial positive, partial negative right here. Okay, so a molecule that is polar will have two poles, a partial positive and a partial negative pole, and very creative, they called it a dipole, okay? And when these polar molecules are placed between oppositely charged plates, they tend to become oriented with respect to the positive and the negative plates, all right? So they will line themselves up. Polar bonds will have a dipole moment. And what does that mean? It's something that's actually measured. You can give it a number even. It's all based on which one loves electrons more. And so it says polar molecules will have a net dipole moment, and the electron cloud will shift and result in these zones of partial positive and partial negative charges in 3D space. So what I would highly recommend you to do right now, I have already linked this video on Google Classroom. You might want to stop this, watch the new video on polar bonds and molecules, all right, and then come back when you're done, okay? All right, see you soon. Bye-bye. Hey, Chemsters, this is Mrs. Vandeloy again. Hopefully you paused this to watch the other video and now you're back here again. So anyway, let's kind of put this idea into action and see how what we have done so far has really helped. So the first thing I want you to do is, will you draw your Lewis structure for water? So pause this if you need to, draw your structure, and then let's see how these idea of dipole moments and whatnot work. Okay, so pause this, come back. All right, this hopefully wasn't too hard. And so now what do we do? Does this have a dipole moment? Well, we got the structure. It is bent. Hopefully you remembered that. And is there an unequal distribution of electrical charge? In other words, are these bonds polar or non-polar? And your answer should be, oh, they're polar. How come? Because oxygen is a 3.5, hydrogen is a 2.1. When you subtract, you get a 1.4. If you go up here, 1.4 fits in this polar covalent bond, okay? So the bonds are indeed polar. So what now, I'm going to draw these vectors, these vectors in here. And why do I have the arrows pointing towards oxygen? Because oxygen is more electron loving than hydrogen, so the electrons are being pulled towards the oxygen. Now, what I need to ask you is, are these vectors, do these arrows, do they cancel each other out so it's like a tug of war, or is there a net force going somewhere? All right, and the answer is there's a net force. The arrows don't cancel each other out. So because there is a net force, so this arrow and this arrow has a net force going this direction, it has a dipole moment. And so what we can say here is that because it has a dipole moment, that we have a partial negative on this side. Why? Because that's where oxygen is. It loves the electrons, and a partial positive here. So it is a dipole molecule because it has two poles, a partial negative, partial positive. It has a dipole moment, which would be really the resultant of this arrow. Okay, so that would be the first one. Why don't we go ahead and draw carbon dioxide? So again, if we have a couple examples, I think it's going to get a little bit easier. So pause this, go ahead and draw carbon dioxide, and let's see what happens here. All right, welcome back. Hopefully you drew carbon dioxide, and there it is. Now the question is, does this have a dipole moment? The answer is, well, let's find out. Are the bonds polar, yes or no? Well, the bonds are polar. Why? Oops, I'm sorry. Because they have what? Well, oxygen is a 3.5, carbon is a 2.5, and so what does that mean? Yes, the bonds are polar. So the arrow is pointing here towards the oxygen, and the arrow is pointing here towards the oxygen. And what does this mean? The arrows cancel each other out. There is no dipole moment. It is not a polar molecule. There is no dipole. So it is an equal pulling. It's like a tug of war, a tug of war pulling on both sides of carbon, and the net result is there is no net force, okay? They cancel each other out, so there is nothing else here. Well, what about methane? Okay, CH4. Go ahead and draw this, and when you're ready, come back. All right, so here's my methane. So what is the first thing I did here? I asked if the bonds were polar. And if you look up on your sheet, carbon is a 2.5, hydrogen is a 2.1. When you subtract those two, guess what you get? You get a 0.4. And what does a 0.4 mean? It's a pure covalent bond. All right, so is there any vectors? Is there any force? Is there anything pulling on this? The answer is no, not at all. So don't draw any arrows. There is no arrows. There is no polar bonds. There is no dipole. You're done. So let's see what the next set is. All right, so go ahead and draw the Lewis structures for these next three. So pause, draw the structures, and then come back, okay? All right, well, welcome back. Hopefully you drew this for carbon tetrachloride. And the question is, all right, are the bonds polar or non-polar? Well, let's go back and look up here again. So we have a 3.0 for chlorine. We have a 2.5 for carbon. So 3 minus 2.5 is a 0.5, and yes, it is. It's still in the range of being polar covalent. So what does that mean for carbon tetrachloride? Well, we can do this. And what does that mean? That the vectors here are going each towards the chlorine. And so what do you notice? All the vectors are going to cancel each other out. There is no place, or there is a larger area of partial positive, partial negative than the other. The vectors cancel out. So there is no dipole moment. Even though the bonds are polar, the molecule is not. All right. So what about this next one? We have NH3. And if we go back and we look at the electronegativities. Find nitrogen, it is 3.0, and hydrogen is 2.1. Subtract, you get 0.9. Well, guess what? You do have, polar bonds. And so what does that mean? That everything's being drawn in here. Now, let me ask you, do the vectors cancel each other out? Well, in a sense, these two do, all right? If these two cancel out, there's nothing canceling this out, so you do have a net dipole moment going this direction. So what does that mean? That you have a partial negative near nitrogen and a partial positive on the opposite side. Okay, so that does work. Now look what happens with the next one. Okay, it looks an awful lot like NH3, doesn't it? But if you go back and you look at the electronegativity values, the electronegativity values are equal to each other. So 3.0 minus 3.0 is 0. There are no vectors. This is a non-polar molecule. Okay, how about the last few? Okay, so how did we do on these other ones here? So hopefully you're able to do this. Oh, do you remember this? This is your seesaw shape, all right, sp3d1. And so here are my vectors, because fluorine, if you remember, is the most electronegative element. When you subtract them out, again, it's a polar. Now the question is, do these cancel each other out? And the answer is no, they don't. So the net result is that, well, the up and downs cancel each other out, but these over here do not. Now, if these were all filled, so it's trigonal bipyramidal, then yes, it would be a nonpolar, but that's not the case. We have a lone pair right here. And what those lone pairs do is they allow for this vector, if you will, this dipole moment to occur, so that you end up having this region over here being partially negative, because that's where your fluorines are, and this region over here being partially positive, because there's nothing there pulling the electrons that direction. They're all going the opposite direction. All right, and then finally oxygen. I don't know if you've already drawn this, but if not, take a few minutes out and draw it. But if you already have, here it is. And what do you know about these bonds? All right, well, they're identical, so 3.5 minus 3.5 is 0. This is a nonpolar. There are no vectors. There is no dipole. All right, so again, this section is very important, where you are able to combine your bond polarity by using the electronegativity differences with your structures. So why don't I quit here? This is a good stopping point, and look for another video which is going to continue on. All right, so see you shortly. Bye-bye.